Okay, good evening, everyone. It's my great pleasure to welcome you all this evening to the inaugural KIPAC public lecture, and a special welcome to those of you watching on the video stream either in the next room or online as well. KIPAC is the Kavli Institute for Particle Astrophysics and Cosmology, for those of you who don't know. KIPAC is a laboratory that spans across the Department of Physics and the Department of Applied Physics down at Stanford, and also up here at the SLAC National Accelerator Laboratory. And it is our mission to combine the studies of astrophysics, cosmology, and particle physics to really understand the origins and the workings of the universe. So I said this is an inaugural lecture, and we'll be hosting these lectures once every month. And we have some great speakers lined up for you over the next couple of months. So on Tuesday, December 12th, Professor Aaron Rudman will be talking about the fastest eye on the sky and what we hope to discover with the forthcoming Large Synoptic Survey Telescope. And then on Tuesday, January 16th, we have Daniel Holtz, who will tell us about hearing the thunder and seeing the lightning from colliding neutron stars. So if you're interested in any of those, do check our website, our Facebook page, and sign up to our mailing list. All the information will be on there. But tonight, I'm delighted to welcome Professor Roger Blandford, who's going to tell us about black holes, neutron stars, and gravitational waves. Then after the lecture, we'll be joined on stage by some of our local experts and members of the teams that were involved in the very exciting LIGO discovery that was announced last month. We're lucky to have Dr. Brian Lantz from LIGO, Professor Risa Wexler from the DES collaboration, Dr. Nicola Omadai from Fermi, and Professor Bob Wagner, who was one of the first to work on gravitational waves. Now, Professor Blandford holds the position of the Luke Blossom Professor at Stanford, and I could give a whole lecture on his achievements, but I'll keep it brief for this evening. He received his BA, MA, and PhD from the University of Cambridge, and then went on to teach physics and astronomy at Caltech for more than 25 years, before he moved here to Stanford to become KIPAC's founding director. He is a fellow of the Royal Society and of the American Academy of Arts and Sciences. He's a member of the National Academy of Sciences, and he chaired the National Academy's Decadal Survey for Astronomy and Astrophysics in 2010. Most recently, Roger has authored a new book with Professor Kip Thorne called Modern Classical Physics. Kip was a founder of the LIGO Gravitational Wave Observatory, for which he shared in the 2017 Nobel Prize in Physics. And also, for those of you who have seen the movie Interstellar, he was the scientific creator for that. And like all good books that cover the topic of gravitation, the book has a substantial gravitational field of itself. So I need not say that Roger is a renowned theoretical physicist, specializing in black holes, gamma-ray bursts, gravitational lensing, the evolution of the universe, and many other things. He's perhaps best known for his seminal work on black holes, but I will hand over to Roger to tell you more about that. So please join me in welcoming Professor Roger Blandford to the stage. Thanks.
Well, thank you very much indeed, Dan, for that very generous introduction. I'm very happy to be here at this inaugural lecture, and it's obviously a very exciting time in astrophysics and cosmology, and I'm looking forward to sharing some of this with you. So, my story really begins with gravity. This here is Woolsthorpe Manor. It's in Lincolnshire in England. It's the birthplace of Isaac Newton. This is where he invented calculus. We know that to be true because you can see the integral signs carved there on the wall. Actually, that was a pretty cruel joke because Newton's great rival, Leibniz, introduced the integral sign. I was born 4 miles away from Woolsthorpe and boast about this to my students. They are not impressed. A well-known myth, there's Newton, there's Leibniz, got rid of him. Okay, a well-known myth is that Newton watched an apple from a tree and he realized that the fall of this apple could be described by the same agency as the orbit of the moon. He invoked an invisible gravitational force to do the job. However, he found this notion very confusing, especially in Latin. He also formulated the mathematics to make these ideas usable. And here are his laws of motion and gravity as mathematics. The equations were the foundations of much of physics until quantum mechanics came along. Fast forward 250 years to 1915, when Albert Einstein formulated his general theory of relativity. Einstein combined 3D, space and time, which are quite separate in Newton's approach, into a single entity called space-time. He discovered that space-time is curved in the presence of matter. He also did away with Newton's invisible force and was able to describe the motion of an apple or the moon as a straight line in curved space-time. Here is Einstein's equation. It looks very different from Newton's law, but the outcome is very similar, and the small differences are actually corroborated by accurate measurement. We now have no grounds for doubting general relativity, so long as quantum mechanics is intimately involved. So basically what we have in this equation here, and let's come back to this point, is some quantity here that represents the curvature of space-time is dictated by the matter that's present. It's just a very simple relation, but of course there's a lot of mathematics that underlies it. The idea of a black hole was first mooted by an English cleric, John Michell, in 1783. He envisaged a mass so concentrated that nothing, not rockets, not light, not superheroes, could escape its gravity. Well, maybe not the superheroes. This was placed in the framework of general relativity in 1916 by a German soldier, Karl Schwarzschild, who also happened to be an observatory director. He found a solution to Einstein's equations. Instead of a small space-time curvature, as made by the sun, see there, he considered a very large distortion. Today we know that it describes a black hole, although neither he nor Einstein fully understood the significance of what he had done. The solution that Schwarzschild found exhibits an event horizon, this is an imaginary surface surrounding the black hole. It is the point of no return. Black holes are mass, and the bigger the mass, the bigger the event horizon. And what Schwarzschild's solution shows mathematically is that black holes can exist. For the next part of the story, I turn to stars. When stars like the sun run out of nuclear fuel, they settle down to become white dwarfs. White dwarfs are about the size of the Earth, and the pull of gravity is balanced by the pressure of cold electrons, obeying the uncertainty principle. Around 1930, a young Indian student, Subramanian Chandrasekhar, showed that white dwarfs have a maximum mass of 1.5 solar masses. Stars much more massive than the sun eventually collapse to a different state called a neutron star, where the electrons are replaced by neutrons. Neutron stars are much smaller. They're about the size of San Jose, about 12 kilometers in radius. The American physicist Robert Oppenheimer showed that they have a maximum mass, which we now know to lie between about 2 and 3 solar masses. We know that stars make heavier collapsing masses than this, and so they cannot resist the pull of gravity. Therefore, we can conclude that black holes must exist. Now let the astronomers pick up the story. In the 1960s, they were able to observe the sky using X-rays. They found a powerful compact source in orbit around a giant star. They weighed the compact source using Kepler's laws and found that it was heavier than 3 solar masses. They were therefore able to conclude that black holes really do exist. Now you might ask, why is this source so very bright? Why can astronomers see it? Why is it not just a lifeless corpse shrouded by an event horizon? The answer is really depicted here. A disk like this, there's a disk, gas leaves the star and orbits the black hole shown there, and it forms a disk around it. So, imagine something like this here. I've got a bag of tricks here, so if we look at that, there's a disk that is going to spin around, there's a black hole there, and this disk here has gas that's moving relative to itself, and there's a lot of friction in this disk. And as it moves, it heats up the disk and makes it hot and causes it to radiate X-rays and ultraviolet radiation. So that's how astronomers can see black holes. They see the gas that's swirling around them. A disk like this can be very thin. It's called an accretion disk. It can be thin like Saturn's rings, or an LP, for those who can recall such a medium. It can also be thick and a torus like a donut. Now, as this gas, the efficiency with which the energy is released by the gas as it spirals inwards under friction, the efficiency of that can be impressively high. It become... That's friction. Okay. That wasn't me. Anybody? There we are. We got it back. Okay, there we got it back. Okay, good. It can be 100 times nuclear power and 1 billion times the mere chemical power of something like dynamite. Now, these accretion disks that orbit the black holes have very strange properties. They can oscillate with characteristic frequencies that you can hear as strange tones. So there's a graph of the X-ray emission as a function of time, and with any luck, you can hear it. Or at least you can hear a transcription of it into sound, and you might have heard a periodic oscillation, which you can see here. That's one of the properties. Black holes, not only can they have disks around black holes, not only can they sing, they can also dance. So here's another famous binary source with a black hole in it called SS423. It comprises a regular star and a black hole orbited by an accretion disk. However, like many of these sources, it also produces a pair of collimated jets, one going perpendicular to the disk in that direction, one going perpendicular to the disk in that direction. And the speeds of the gas that flow outward in these jets are typically quite close to that of light. We'll see a lot more of these jets in a moment. Now, these SS423 jets are unusual as their direction changes over 5 months. And this leaves a pattern on the sky, like that. So it's a bit like watering the garden with a hose pipe. It used to be a forbidden pleasure. So you can imagine that's the black hole like that, then you've got 2 jets like that, then it's going around like that. These are obviously observations. So, let me return from observation to the theory of black holes, and I want to make a few important points about them. If you were to watch someone falling into a black hole, it would appear to take an infinite time for them to cross the event horizon. So, I've got here, we used to use graduate students for this, but that's not allowed anymore. So I have here a Lego toy like that, and we're supposed to be yes, I have to be a black hole, I remember that. Can you hear me? Can you hear me? You shouldn't be able to. Ah, there we go. This doesn't work with real black holes. Yeah, okay. So let's do that there. So here we go. Now, I have to be over here. There we go. Okay, I was told to stand here. Okay, all right. Now, here's my little Lego robot. It's obviously a Lego toy. And of those of you, the movie Interstellar was mentioned. I'm going to call it Kip, who is the robot in the movie. I have no other reason. Okay, so it's going to come down like that. And what you would see is the light, maybe radiated by this falling intrepid Lego explorer, getting dimmer and dimmer and redder, and if there was going to be a flashing pulse light, what you would see is, from a distance, is the distance between the individual pulses, which might be irregular as far as the Lego Kip is concerned. The distances between the pulses would be we've got the movie. Oh, we didn't get the movie. That was the problem. It seemed to be. I think we have to go back. We've lost the slide. Can we get back onto the? Okay. That's right. Okay, there we go. So this is what was supposed to happen. Yeah. So you can see the by falling in, and if you're pulsed regularly from the Lego toy, if you pulse regularly, then what you would see is the spacing between the pulses getting longer and longer. And eventually, you'd see no more, but in a formal sense, you would never have crossed the event horizon. You would never see the Lego toy Kip cross the event horizon. Now, let's go on. And many scientists at the time, it's quite surprising, said that black holes should never form, and therefore somehow or other they didn't exist. And the fallacy in this interpretation was pointed out by John Wheeler, who's shown here, and he's the man who popularized the moniker black hole, and his colleagues, about 50 years ago, worked out a lot of the properties. And the key point there, there's obviously a lot more going on here, but the key point there is that if you look at it from Kip's point of view, as it crosses the event horizon, so you come in like this, and then there it's gone, the event horizon crossed like that. For Kip, the time that it takes to cross the event horizon is decidedly finite, and what happens next is that after you cross the event horizon, at the point of no return, the time that you take to get to the center of the black hole, where there is essentially a singularity, the time that it takes is very finite, and so it is a very real problem for Kip that they really have approached a black hole and gone over to the other side. And in the case of the black holes I showed you about, it would just be a very short space of time, and they would then get to this singularity when tidal forces would tear them apart, and then in a very real sense, that would be the end of time. And from the point of view of a theoretical physicist, we don't know what to do. So that's the tidal forces pulling you apart. So that works quite well with Lego, you see. Okay, so let's go on there. Now, this anarchic state called the singularity is in a very real sense, it's the end of time. Now, there was much more that was understood around this time by Roy Kerr, by Roger Penrose, Stephen Hawking, and many others. They discovered that the black holes we expect to observe with telescopes are really very, very simple. They're all surrounded by event horizons and described by just their mass and their spin. There's Roger Penrose, there's Roy Kerr, there's Stephen Hawking. And the two parameters that you need to describe these black holes are basically just their mass and their spin. You might say, how do you know what a spinning black hole is? Well, a black hole has no features. I've got to make sure there's nothing showing. Here we go. There we go. And here's the situation. So here we go like this. Now, you might say, if I'm a black hole like that, you can't really see which way I'm pointed. There's no mark on it. However, if I have my good friend, good robot Kip, come in like this and just hover above the horizon, he needs enormous rocket boosters to do that, but if he can do that, he finds he can only move around in one particular rate of rotation, and that rate of rotation is the rotation of the rate of rotation of the black hole. So it is operationally well defined. Now, Roger Penrose discovered something else about spinning black holes. Their orbits very close to the event horizon of the black hole, that where the E equals mc, the energy of a body on that orbit, including the E equals mc squared rest mass energy, when that energy is negative. So what that means is, if you throw something onto that orbit and let it cross the event horizon, you'll add negative energy and negative mass to the black hole. It will slow down. It will lose mass, lose energy, and that comes from the rotation. The black hole mass will decrease. Now, we can't do this easily, but we can at least do it as a thought experiment. Again, we'll use KIP to do this. So what we've got there, as you can see in that movie, is the KIP went down to the black hole. We'll just use one hand. It went down to the black hole like this and went down with his rocket ship attached to it like that, came in like that, and then kicked off the rocket ship into the black hole with negative total mass, and by conservation of energy, KIP had positive mass. And so the positive mass he could carry away. So what you're doing with this accountancy is you're extracting energy from the spin of a black hole. So what we can say is that black holes ain't so black, after all. And there's a lot of spin energy there available if these black holes are spinning as fast as the astronomers believe that they are. So let's now go back to astronomy. The black holes I've discussed so far are not much more massive than that of the Sun. There's another type of black hole that astronomers observe, and these are called massive black holes. It turns out that essentially every normal galaxy has a massive black hole at its center, just like every atom has a tiny nucleus. Although the black hole is massive, its size is really very, very, very tiny. It's no bigger than the solar system, sitting in the middle of a galaxy. Our galaxy is no exception. There's our galaxy, seen from a distance, of course. There's the center of it. And here is some stars that are seen orbiting a compact mass at the center. And if I can just get this started. See there. These are real observations, although they're actually projected forward for about 8 years from where we are now. But these are stars that are observed orbiting a compact mass at the center of our galaxy, and we have every good reason to believe that it's a black hole with a mass that's about 4 million solar masses. 4 million, not just a few times the mass of the Sun. Let's look at another galaxy called M87 at the center of the Virgo cluster of galaxies. Its black hole mass is 6 billion, that's billion, not million, solar masses. And it grew by swallowing gas, stars, and smaller black holes. The most obese black hole we know today is 20 billion solar masses. Clearly it ate too much, and young people should be warned. The M87 black hole has an accretion disk, and it launches 2 jets. This was the very first example of a jet that was discovered over a century ago, just down the road from here on Mount Hamilton. So there's M87, and you can see a feature going out of it at the bottom right-hand corner. It's rotated in this image. This is a Hubble image. That's an X-ray image with Chandra. That's a radio image. You can see that one jet there coming out of the black hole, which is located here at that's where the location of the black hole is. And then if we continue down this path like a Matryoshka doll, those are high-frequency radio observations, and those are nearly millimeter observations. And what we are able to do with radio telescopes is to resolve structure on the scale of about 30 times the size of the black hole already. So this is a very exciting prospect. We look on smaller and smaller scales with going to higher and higher frequencies, and we are starting to resolve what's going on really around the black hole. Now, here's another, let's move on to that. Now, the black holes in the galaxy and in M87 are very fussy eaters. They are given meager rations by their cruel galaxy that hosts them, so they get very little gas, and they aren't able to shine very brightly. We only observe them because they're very, very close. Don't feel ashamed of the black hole in the center of our galaxy. You wouldn't want to live at one that was a heavy eater, that was being fed very well. In that case, it would look like 3C273, and this is the first so-called quasar that was discovered in 1963, and the accretion disk and the jet are hundreds of times brighter than the galaxy that hosts it. And this is a black hole with a disk around it, making jets, and it's not much bigger than our solar system, about the same size of our solar system, right in the middle of the galaxy. And we can see, move back there, sorry. You can see on the right-hand side, you can see, if you block out the quasar right in the middle, you can just about see the galaxy around there with Hubble Space Telescope. Now, when these, you might ask, why do you only, in these sources I've shown you, why do you only see one jet? The answer is a very important part of the story, is that when the jet is moving with a speed close to that of light, as most of these are, and is pointed towards you like that, perhaps another one in the opposite direction, the one that's pointed towards you will be extremely bright. By moving in your direction, special relativity allows it to make a very much brighter feature there, and so that's, in fact, moving with a speed that is within a few percent of the speed of light, this material flowing out here, and we see these very bright features coming towards us. So there's only a small fraction of all of these quasars and their jets that are pointed in our direction, but they are prominent because they are brightened so much. We call these objects not quasars, but blazars when the jets are pointed in our direction. There are many more jets launched by massive black holes. Here's just an example. There are thousands of them. I think every one of these here tells a story, which I'm not going to tell here, but they're, I think, very beautiful, but they're also very revealing about the physics of what's going on in these sources. Now, black holes are commonly portrayed as invisible cosmic vacuum cleaners, one-way membranes. However, as we've seen, they can be very luminous. They can launch powerful jets and outflows. This is an X-ray image of the hot gas that surrounds the central galaxy in the Perseus cluster. It's not a leftover from Halloween. The dark regions, you can see here, There's one there. They're actually giant bubbles that are floating away in the gravitational field surrounding that galaxy and in the cluster, and they've been inflated by jets from the central black hole. It's not hard to imagine that the quasar, and especially the jets, can inhibit the growth of stars around here. So in a very big way, they have a large part to do in the ecology of the universe. I mentioned that black holes were described by their spin as well as their mass. Spinning black holes allow gas in the accretion disk to orbit closer in and to move faster. It's not too easy to see here, but basically what is going on is that this is a black hole that's not spinning very fast, and this is one that is spinning very fast. And we know that the gas that orbits around it in an accretion disk can get closer and closer to the event horizon, which is there, in the case when it's spinning rapidly, than when it's not spinning. And therefore, when we look at this high-speed gas and look at the emission lines from it, the Doppler shift operates, and we get a very broad line, and we can distinguish the rate of rotation in this case and the rate of rotation in this case. And so that way, we have not just a measurement of mass, we also have now a measurement of spin. There are other ways of doing this, but this is a particularly fine way of measuring the spin. And the bottom line is the black holes seem to have a very high spin. We can now discuss how black holes are made, how the jets are made, I've explained that accretion disks orbiting black holes glow because of the friction that the gas, as the gas spirals inwards. The friction turns out to be due to the magnetic field that is attached to the gas, in much the same way that magnetic field lines are attached to the Earth. One of my scientific heroes is Michael Faraday, shown here. And nearly 200 years ago, he showed that moving magnetic field lines make electricity. This can also work with accretion disks and black holes. And the ones in galactic nuclei can generate a voltage. So there's a disk there, something's called a Faraday disk. There's a magnetic field there, there's a magnet there, and then it'll light up a light bulb. So that's the basic idea. And in this particular case, though, when you figure out how much the voltage is, it can be 1 billion trillion volts. Furthermore, we know that the resistance of a black hole is about 100 ohms. And so you can use Ohm's law, which many of you will recall there, to calculate the current and the power. So these massive black holes in the nuclei of galaxies, when they're spinning rapidly, when they've got magnetic field, as they inevitably must have, will create current and voltage, and they'll create a lot of power. And that power is enough to power the emission that you've seen and to make those bubbles, for example, in the Perseus cluster. Now let's take time out from black holes and return to this other compact object I mentioned, the neutron stars. The first clear detection of one was made in 1967 by Jocelyn Bell in Cambridge, a graduate student at that time. I know about this because I was an undergraduate then, and I heard one of the first talks on the discovery given by her advisor there, Tony Hewish. She found persistent radio signals, and it quickly became clear that these were associated with a spinning neutron star endowed with a strong magnetic field. The spin periods of pulsars that we know today, this is the first one, which is a fairly regular pulsar, but we now know about 3,000 or 4,000 of these. The spin periods of those range from 1.5 milliseconds to nearly 10 seconds. The magnetic fields that these pulsars have associated with them, rather like the magnetic field of the Earth, but typically 1 trillion times more stronger, maybe about 5 trillion times stronger than the magnetic field on the Earth. And it's that strong magnetic field and the voltage that the moving magnetic, if we've got magnetic field, let's let this be a neutron star for the moment. We can make this be a neutron star. And so we can spin it like that. And the magnetic field lines get swung around like that. So according to Faraday, they will make a voltage. The voltage in that case is about 1,000,000 billion volts, and for a typical pulsar, and that will make a lot of power, and that's how we can see objects like the Crab Nebula. So as well as being fascinating in their own right, these neutron stars have turned out to be wonderful tools for astrophysics. They've been great cosmic laboratories. And the main reason is because as they spin, and the magnetic, if you imagine the magnetic field line coming like this, then maybe do it like this. If we just imagine an observer, say, over there, if I just spin around like that and then come back again, then the observer over there will see a pulse and then come round again. And not the way I'm doing it, but the way a pulsar does it. They are extremely good clocks. And that very high accuracy of those clocks means that we can use them for experiments in gravitation and for probing what's going on in the space between the neutron stars and us. Here's an example of this. This is a pulsar here that is a spinning magnetized neutron star making pulses of emission that are seen by telescopes, but this one was the first example of one that was in a binary system. And it has a neutron star companion. The spin period of the pulsar is about 60 milliseconds. The period of the orbit is about 8 hours, a third of a day. And you can measure the masses to be about 1.5 times that of the sun, which is just about right for neutron stars. And Bob Wagner, who you'll hear about later, and I and several other people at this time, when it was discovered in 1974, were helped to make the theory that could be used to analyze the system. And in particular, there were some special things that were done with it and have been done now. You can do lots of tests of relativity. You can see lots of effects of relativity, and we'll exhibit them here by plotting the measurement of the mass of one of the components in the binary, and there's a measurement of mass of the other. And if you blow up this region here, you can see with extraordinary accuracy that all measurements give exactly the same answers for the masses. So that's a way of saying that general relativity works extraordinarily well here. But there's something even more important that happens, and that is that a binary pulsar will radiate gravitational radiation. And I'll say a lot more about this just coming up, but let me so basically what happens is that a binary neutron star has got two neutron stars, let's imagine like that, and they're going to orbit around like that, and they're going to create gravitational waves. And those gravitational waves are going to gravitational waves can be detected, and by the shrinkage of the orbit in the system, and what we found was that the orbit was getting smaller and smaller as the waves were carrying away the energy, and we could predict that it will merge in 310 million years. And this is a measurement, essentially, of this period of the orbit, 8 hours, made with extraordinary precision because pulsars are such wonderful clocks. This is over a period of time, and of course it kept on doing this in 2017, and there are other examples. The bottom line here is that the prediction for general relativity makes for the rate of loss of energy, and the change of the period of the binary agrees with observation to better than 1 part in 1,000. That is a remarkable testament to the theory of general relativity, and one of the main reasons why, for some time, people have believed it is the correct theory of gravity. The next topic I want to bring up, and I'm going to bring this back together again in a moment, is another phenomenon that was found. And this is the phenomenon of gamma ray bursts. These were discovered in the 1960s by scientists who were actually looking with satellites for evidence of illicit nuclear tests. They found these bursts all the time, and thankfully they did not confuse them with nuclear tests and found that they were quite extraterrestrial. A lot has been learnt about them since then, and I can't describe all of this. I just want to cut a long story short. And astronomers have shown that most of them belong in one of two classes. One class is a burst, a flash of gamma rays that we can actually see right across the universe, and it has a duration that is longer than typically about 2 seconds. So long in this case means more than 2 seconds. The second class is somewhat similar, but also can be distinguished, and they're the flashes which are also very distant, have durations that are typically less than 2 seconds. And we now believe, there's good arguments for belief, that they have rather different origins. The ones that are longer than 2 seconds, the long bursts, they are associated with supernova explosions. These are the end of life of massive stars, and they disseminate most of the elements that are made out of which you and I also are constructed, and these supernova explosions, and a minority of them have a black hole, almost certainly in the center, a disk of gas orbiting it, and they make a pair of jets. And those jets are so powerful, they punch a hole through the star, and they're able to escape from the star. And then when they're pointed towards us, just like the blazars, when they're pointed towards us, they are very, very bright. And that's what gamma ray astronomers are able to detect. By contrast, it was conjectured that the most likely explanation for the short bursts was the end point of one of these binary pulsars. It's 310 million years for the one that Hulse and Taylor found. They orbit together, and then eventually they're going to merge as two neutron stars. It's conjectured that this was the explanation for the short gamma ray bursts. So we brought the black holes and the neutron stars together in one phenomenon with two types of explanation, the black holes and the neutron stars. So let's just quickly recapitulate. We have good evidence that general relativity and basic astrophysics are correct. And as a consequence, spinning black holes and neutron stars are forming, and we're observing them. The neutron stars are seen most readily as pulsars, but in many other forms, in fact. And the black holes are seen quite often as X-ray sources and in the nuclei of galaxies. When black holes jets are formed, they like that, then the jets are formed, and when they can be very bright when they're pointed towards us, and we call these blazars. And when a newly formed, when it's a neutron star, when they orbit about each other, they can radiate gravitational radiation, and that gravitational radiation quantitatively agrees with the general theory of relativity. So at this point, I should probably start talking about gravitational waves. So here's just a still for gravitational waves. Here are two masses as they orbit around each other. So if you think about the source, I've brought two very heavy books here, so you can see. So there they go, and they're going to orbit around each other like that, and they're going to generate gravitational waves. don't worry, it's not an awful lot of gravitational waves in that case, in spite of the weight of the book. Now let's think about how we might detect that. You might say, well, what is a gravitational wave? What does a gravitational wave do? So I'm going to use the same device. I'm going to say, let's have two masses like this. Let's hold them out like that. Maybe I should do it like that. There we go. Two masses like that. And then let a gravitational wave pass by it. So I'm going to have two heavy masses. They're going to be free, so my arms are not, I'm just going to let them float around, but I've got to hold them. So let's imagine they're just suspended. If a gravitational wave goes by, it will do that, like that. And in fact, it isn't just in one direction, because there's also a second motion that'll be up and down. So it'll be like that. Like that. That's one type of gravitational wave. There's another one that's rotated through 45 degrees, but I need several drinks before I can actually perform that one. So this is what it does, like that. And I think this is the first time a physics book has been plugged with an exercise video. So we have detectors, and here we use LIGO, and LIGO has been a truly wonderful experiment. I have to say, going back to my spaceman, I always thought it should be, where is he? Here he is. I always thought it should be called Lego, because the people who were working on it when they were my colleagues a long time, I still are my colleagues a long time ago, were always taking it apart and putting it back together again. And so I thought Lego would have been a good name for it, but they called it LIGO, which is fine. And basically, the major facility in the United States comprises two detectors, 2 arms, 4 kilometers across, and the books here are replaced by mirrors, and there's a pair of mirrors in that arm and a pair of mirrors in that arm, and this sort of motion like that you can see by the movement of the mirrors. You might say, well, it's a big motion like that, so that's good, except the motion that is actually measured using lasers is very, very small. It's about 1,000th of a proton is what they can measure. And this is truly extraordinary technical achievement. It took nearly 40 years to do, and I'm very proud to say that my colleagues at Stanford, led by Bob Bayer, who was one of the first people working on this project, he's here in the audience, and also including Brian Lance, who will be on the panel, have been quite at the center of this wonderful facility and the discoveries that it has made. So there are other facilities. There's one in Italy, Virgo, which is now near Pisa, which is now coming online, and that actually contributed to the recent discoveries. And there's a network. Some of this is incipient, some of it are somewhat former facilities, but all of it represent new technical developments that will make this, we hope, an even more sensitive. So, the first detection of gravitational radiation was a truly exciting event. It happened on September the 14th, 2015. And we now know that it comprised a 36 solar mass and a 29 solar mass black hole in orbit about each other, making a single 62 solar mass black hole. Now, those of you who are good at arithmetic might have observed that 29 plus 36 does not equal 62, but equals 65. The extra 3 solar masses were carried off as energy by the waves. This is E equals mc squared on a grand scale. This is a plot representing the measurements of the relative motions of the mirrors between the 2 arms and the 2 detectors, the one in Washington, the other in Louisiana. And it's very clear that it's a very strong signal. It was surprisingly strong for the first detection. So these 2 black holes clearly orbit each other faster and faster. They engaged in this diabolical dance that ended with an oscillating space-time that quickly relaxed to form a single stationary black hole with its stationary event horizon. the gravitational power exceeded that of all the stars in the universe by a significant factor at the end of this merger here. Let me just show you a movie now. So the peak power is that. There you go. So we've got now 3.5 other examples of that. The half is, so there we go. So there's a movie. This isn't an artist's impression. This is a calculation, and I like this one because I like gravitational lenses, and it shows what the stars in a background stationary star field would look like if you were foolish enough to be that close to it. You see that? And you see the single black hole now forming and shaking around, and you saw the waves, and now it's all settling down. There's a little bit of motion, see there, and so on. So that was a real technical achievement, not just to do the experimental work to make the detectors, but also to compute these space-times. Now, exciting as those 4.5 detections we now have of binary black holes are, gravitational wave astronomy took another leap forward on August the 17th this year. In this case, the first example of the source that had been expected all along, which was the binary neutron stars, was found. And instead of having to wait 310 million years, we only had to wait 43. Actually, what was seen first was a short gamma-ray burst by Fermi Gamma-Ray Space Telescope. And so it's a short gamma-ray burst like that. It was slightly different from the ones that are normally observed, but it was enough to make a detection and draw everyone's attention. And then, looking essentially simultaneously in the LIGO waveform, they found a pulse like this, just 1.7 seconds away from this. And Nicola Olmodel and many colleagues, part of Fermi Gamma-Ray Space Telescope, that were able to make this detection and bring about this temporal coincidence. Now, with further analysis, it was possible to see the frequency of the gravitational radiation, and that frequency of the gravitational radiation got faster and faster, higher and higher as time went on, until eventually there was the merger and 2 black holes were seen. So let's just go on. And what happened? And it was able to show that the masses were indeed those of two neutron stars. Now the story then got very interesting in that as part of the way of developing this type of observation, the positions and what information was known at homes and so on were communicated to a large consortium of astronomers with telescopes, looking from radio waves through gamma rays and so on. Everybody, even the neutrino astronomers, had a look. Everybody looked. And it was possible, it's actually a remarkably successful venture, to narrow it down to a few hundred, perhaps, galaxies. And one was found where there was a new source, and it was quickly determined that you had actually seen, after the merger of the 2 neutron stars, you had seen an optical display associated with gas that had been flung off from the 2 neutron stars and was able to glow and be seen by optical astronomers and eventually by X-ray and radio astronomers as well. And again, we have some local interest in that we're major partners in the Dark Energy Camera, which was one of the first telescopes that saw this and was able to make the identification with the galaxy. And Risa Wexler, who's going to be on the panel later, is representing many people here who work on that collaboration. So move on. This is an example of what we might call multi-messenger astronomy, because with a detection like that, that's how long the gravitational waves were seen for about nearly 100 seconds. The gamma rays were seen there. The X-rays were seen there, the ultraviolet, the optical, the infrared, the radio, and there were important and useful upper limits from various other types of telescopes, as I said, including neutrino telescopes. So basically what happened, I hope this works, is that this is a simulation. Again, this is a simulation. And this isn't the actual data, this is an actual system, but it's one very similar to it. And you can see the two neutron stars, which are minding their own business, getting closer and closer. But then as they're finite bodies with real internal properties, you can see the frequency getting shorter and shorter. Then they merge, gas gets flung off. This is actually a calculation. And that gas that's flung off is what you're seeing glowing. That's a bit later when the optical astronomers actually could see it. Now what was left behind, we're not entirely sure, because two neutron star masses with some gas flown off could still be another neutron star, but I think we're probably, I would say 9 out of 10 confident that it's really a black hole that was formed here. There's no evidence for a neutron star, but we'll know more as more of these systems are discovered. So this was a truly remarkable discovery in its own right, but it's even better than that because there's a lot that comes with it. One of the things you can do, because you know the strength of the waves, you believe in general relativity, and you can get the so-called redshift or velocity of recession of the galaxy, and that enables you to measure this famous Hubble constant, which determines the size and age of the galaxy. And so this is one determination of the Hubble constant from the microwave background, and they think they have measured it very accurately. Here's another consortium of people, in fact it's several groups, who think they've got something rather different. So there's a bit of a dispute here as to what the Hubble constant is. They think they've measured its accuracy, they think they've got a different answer. And say, well, what's gravitational radiation done for us lately? So this is what that's done. So that's not, really competitive. It's not very good as a measurement. But this is one measurement. Okay, this is one measurement. Imagine there are several hundred of these. This is going to be the way to do cosmography. If several hundred that look like this can be done, it's going to be extremely accurate, and it's going to be a very competitive way of understanding the acceleration of the universe and so on. It remains to be seen if that's possible. Sometimes we call these things cosmic sirens. That's the phrase that's be or standard sirens, and that's and there's a lot of promise in this. Again, we don't quite know how it's going to pan out, but it's be very exciting to find out. Another thing that you get is nuclear synthesis. The origin of the elements. This is a graphic that's beloved by chemists. It's called the periodic table. And it's well known that the early universe was able to account for all of the elements here, except those from lithium down to plutonium. So, and those of you who are composed of helium should be grateful to the Big Bang, but the rest of us are dependent on stars. And there's some boron comes from cosmic rays, and beryllium, I suppose, too. That's for us, yes. But figuring out the general principles was in 1957, but there's a large class of elements, the ones here that are shown here in purple, that the nuclear physics was understood. They required a rapid neutron capture, so rapid a neutron, these neutron stars, merging neutron stars can do, and it was long ago conjectured that they were the source of all of these elements here. I was at the press conference when all this was announced, and it was a very exciting time. I can't really convey fully the excitement of it. It really was tremendously exciting, very innovating, and much was made of the fact that silver, platinum, and gold are made in this way, and so it was called cosmic bling. So also uranium, of course, and plutonium, and so I think you can take issue probably with the details of this graph, but it's really remarkable now that we have a very good story. It's not the supernovae that are making these purple R-process elements. It's the merging neutron stars. There seem to be almost enough of them. Okay? All right. So let's go quickly on. In fact, there's some evidence. It's a little bit shaky at the moment, but there's some evidence, I won't really make a lot out of this, that these elements are actually seen in the spectroscopy of these of the kilonova. And if we just go on like that, they're called kilonova, these objects. and there seems to be some evidence that they're there in that. So if we just go on now to ask about, well, what the future holds, well, in gravitational astronomy, LIGO is going to come back online in a year with, one hopes, very much improved sensitivity and an even greater rate of discovery. So that's very exciting, but there are other techniques doing a sort of LIGO in space called LISA. That may take another 15 years or so, have to wait and see. But there's another technique that uses these pulsars, and timing the pulses from these pulsars is a detector of very long wavelength gravitational radiation. And this is sort of on the threshold of measuring a background from binary black holes. Again, it's pretty close to where one might expect a signal. We'll have to wait and see. There are other, more excitement. There's high-energy gamma rays. There are telescopes that are used to measure high-energy gamma rays. Here's one in Arizona called Veritas. There are many others and more being built. These are photons that have energies 1 trillion times that of optical photons. And again, it is quite possible. Well, we see the blazars are prominent sources of these gamma rays. And we've learned a lot about the blazars from these gamma ray telescopes. So these are merely high-energy gamma rays. There's the very high-energy neutrinos. These have energies 1 million billion times that of an optical photon, these neutrinos. And this is the facility at the South Pole called IceCube. That's a rather heroic place to work, but people do. And they've made discoveries of extrasolar system neutrinos. And again, there's a big puzzle as to what the source of this is, but recently there has been a claim, it's only a claim, it's not more than that, of an identification with a blazar, and so we'll have to wait and see how that works out. Then if we go on to the ultra, not very high, but ultra high energy particles, these are the cosmic rays, these have energies up to 1 billion trillion times that of an optical photon, and they could be made by the blazars themselves that I've talked about. Here's another miserable place astronomers work. It's the Pierre Auger Observatory in Argentina. It's actually fantastically beautiful. I've been there, and the energies of the individual particles at source are those of a well-hit baseball. Okay, a subatomic particle with the energy of a baseball. Think about it. Okay, something else that's going on, big excitement now. Again, this might be part of the story. Many of us believe it's the neutron stars that don't have mere trillion times the Earth's magnetic field, but 1,000 trillion times the Earth's magnetic field. They're magnetars. These are bursts that are seen about once every 10 or 30 seconds right across the universe, created with durations of about a millisecond. Truly remarkable. Fast radio bursts. Again, they'll teach us about the neutron stars. And there are also many great tools for understanding the universe. Here's another thing that's going on. This is the Event Horizon Telescope. This is the sort of supreme experiment to look at our galactic center and that galaxy M87. Here's a consortium of telescopes that are using millimeter observations, and you have a very high angular resolution, and you should be getting within maybe about 3 times the size of the black hole. You're starting to see resolve these black holes. It's truly remarkable. That's the ALMA in Chile, which is one of the anchor telescopes there. This is what a theorist thinks that it will look like. So they're way ahead of the observers. And here's what Interstellar thinks it will look like, and they're way ahead of the theorists. So actually, this was calculated. I know. This was actually really calculated. Okay. So I want to finish now and make some sort of general sort of summary points, if you like. And it's particularly epitomized by this recent August discovery. And you're going to hear more about this from Daniel Holtz in next year. But I'm going to basically try and summarize by reaching for an old and tired cliche. And I'm going to call for the glass half full and the glass half empty. There's a half-full part which comprises validated but not proven conjectures, they include the affirmation that general relativity is correct when gravity is strong and rapidly changing. That is a remarkable discovery. It's not a complete proof, but certainly validation of it. It's shown that light, for example, and gravitational waves travel at the same speed. That's what we expected, but to demonstrate it for free is great. confirming that short gamma ray bursts are probably merging neutron star binaries. Again, that's a great thing. It was a conjecture, and it looks like it's right. More observations will confirm it. Showing that they're also the source of the cosmic bling. That's a pretty big development too. And demonstrating that in principle, and we hope very much in practice, they can be used to measure distances with higher accuracy than other measurements. Now there's the half-empty part. The half-empty part is what I would call discovery space, where there are still many plausible outcomes. These include making more investigations of general relativity using the Event Horizon Telescope and merging black hole binaries. We're going to learn more from that. We expect that it will be consistent with relativity, but there's still a lot of physics going on, and we can learn. If you can image it, that's wonderful. Filling in many of the gaps in our understanding of nuclear synthesis, seeing if this story that the R-process elements are made in binary neutron stars is correct. Gaining new insights into jet formation by spinning black holes. Again, we're going to learn a lot about that too from these sources. Identifying the neutrinos, the gamma rays, the high-energy gamma rays, the fast radio bursts, and so on. All this multi-messenger astronomy is really coming of age. And learning something I haven't really had time to talk about is the hardness of nuclear matter. When you get these two neutron stars that rip each other apart when they get so close to one another, the way in which they do that is dependent on how squishy the neutron star matter is. It's nuclear matter. We have no way of calculating or measuring that experimentally, but it's a very fundamental measurement. And it will, in the course of time, be measured by these merging neutron stars, we believe. And then finally, I think a very exciting possibility is how the highest energy particles are accelerated. So there's a lot going on there. As I say, the glass half full and the half empty. And I personally feel privileged to be around at a time when so much is being understood and there is so much more that is discoverable. I'd like to just finish with a generalization and a caution. Modern science is prosecuted in many ways. At one extreme, there are large multinational corporate endeavors, like the Large Hadron Collider, with a workforce of up to about 10,000. At the other end, we find pure mathematicians, often working alone. All subfields of science are seeking the optimal balance in the space between these two extremes. The direct discovery of gravitational waves provides a telling example. LIGO was bravely supported by the National Science Foundation and several universities led by Caltech and MIT, and including Stanford, for over 40 years. Through many vicissitudes, as it struggled to achieve sensitivity to see the neutron star sources that had to be there and to discover the binary black holes. 1,000 names are on the discovery papers, and they all had to work hard and together. However, the follow-up in August to the neutron star surprise also required a motley crew of observers working throughout the entire electromagnetic spectrum and beyond. Some with access to expensive facilities like Fermi, others using very small telescopes, and the amateurs are going to be in this game before long. They communicated effectively. They, not a committee, made smart choices in real time. They collaborated, they cooperated, and they competed. They found the source and were able to study it before it faded, and they have learned much and are ready for the next example. Astronomers have always known that it is important to maintain a balance between the nimble and the steadfast, especially in the training of younger scientists. The seed corn must be protected from large and hungry collaborations, just as the lions who roam Silicon Valley today need the startup culture to keep themselves healthy. Science in general must champion an entrepreneurial and adaptive component that is expected to find the unexpected, to make mad pursuits of logically unscripted discoveries like pulsars, and to be allowed to fail fast. And my caution is that I hope that in our zeal to raise funding for large, ambitious projects and to demonstrate managerial efficiency, we're not also losing sight of this larger need, and we can learn an important lesson from LIGO. So thank you very much for your time and your attention. Thank you.
Okay, thank you very much, Roger, for a fantastic talk and those important thoughts at the end. Now, I'm sure Roger has inspired a number of questions amongst you, but we'll save those until we have not just Roger, but 5 expert scientists up here on the stage. It'll take us just a couple of minutes to move some furniture around. So a little hint, for those of you who would like to sneak out unnoticed, now is a good time. And a little bit of housekeeping for the Q&A session. Each of you should have a black microphone on the desk in front of you. If you have a question to ask, we ask that you raise your hand. Don't touch the microphone until you are invited to ask your question. But then once you ask your question, if you press the button on the front of the microphone, pull the microphone down towards you, then everybody, including people watching on the stream, can hear. And those of you in the overflow room, if you have any questions you would like to ask, we've got some seats freeing up here in the main auditorium, so if you'd like to come across the corridor, you are more than welcome.
Okay. Okay, so we want to get... I'll take that one, yeah. So here are some books that might be of interest to different aspects of what I talked about. Okay. So, start? Okay. Yeah. Okay, so we can start now. Let me first introduce Brian Lance. A scientist working here, worked for I think nearly 20 years on the LIGO project, and here's a slide he produced to summarize it. So Brian there, and so he's going to handle the instrumental parts of the questions. And then next there's sorry, I couldn't see it here. Yeah, there it is, coming up here. Yeah, sorry. Got lost here. So this is Risa Wexler, who was on dark energy dark energy survey, I should say, which uses the dark energy camera, which is a wonderful camera that's operating in Chile, and that was one of the telescopes that made the discovery of the merging neutron star. Next, we've got Nicola Armadale. He's worked for a long while in Fermi, and he's representing the discovery of the gamma ray burst that followed, in retrospect, the gravitational radiation event by 1.7 seconds. And then finally, Bob Wagner is here, who is an early theorist working on gravitational radiation, and Roger Amani hoped to be here too, who represents neutron stars in some sense, but wasn't able to make it. So that's to show that we do real calculations in theory, but Bob will not explain that. I think I'm just going to start myself by asking each of the panelists just to introduce themselves, to say what it is that they are most looking forward to within the next 5 years from all of the topics that I've talked about here. So Brian, do you want to start?
I'll start, okay. So I'm Brian Lance. I actually work on the LIGO detector. The thing I guess I'm most looking forward to in the next 5 years, we have to be really lucky, but we've been a little bit lucky so far, so maybe we'll continue to be. I'd really like to see a supernova. The black holes and the neutron stars, people have a pretty good idea of what the gravitational waves from those should look like. But the calculations for the core collapse of a big supernova, people don't know what those are going to look like. And so I'd really, really like to see one of those.
So Bob, do you want to say what you're looking forward to?
Well, within 5 years, a different type of source, a rapidly rotating neutron star, can produce a single frequency gravitational wave, okay? Which in some sense is easier to detect. And you can produce these CW waves in 2 ways from rotating neutron stars. They can have bumps on the surface, and they're rotating with periods of a few milliseconds or greater. and that produces a single frequency. Or you can accrete angular momentum from the accretion disk and radiate it in gravitational wave angular momentum, producing a steady state, a converter of angular momentum from the accretion disk into gravitational waves. If conditions are right, which is not at all clear, if they're correct, if neutron stars have the correct composition, you can excite the analog of magnetic quadrupole radiation due to currents inside the neutron star and produce continuous gravitational waves. And they've been searched for in LIGO already in SCO-X1, a powerful X-ray source, and they're within a factor of 5 of our predictions, so we'll see what happens.
Hey, Risa, what's on your list?
First let me just say that, so I'm Risa Wexler, I'm a cosmologist, and so I am really excited about what gravitational waves will do for cosmology. They're just cleaner, the physics is cleaner than almost anything else in the universe. And so if we can measure, 100 or a few hundred of these, we really will get a very beautiful measurement of how the universe is expanding and how that's changed over time. So that's very exciting. But I have to say that I actually am most excited about just whatever we're going to discover that we haven't even thought of yet. I think the most exciting thing about gravitational waves is that they touch on so many different areas of physics, nuclear physics, astrophysics. It's just beautiful. So that's what's most exciting to me.
Okay, Nicola.
Hi, yes, I'm Nicola Modei. I'm working in Fermi, so I'm definitely interested in detecting the electromagnetic counterparts of these objects. We got the first neutron star event right, so we detect a signal with Fermi. We are for sure looking forward to detect electromagnetic signal also from other classes of object, neutron star black hole or even black holes. We expect to have many more of these events in the next 5 years, and since Fermi is very prolific in detecting short GRBs, we also are looking forward to have enough population to study this event.
Let me add my 2 cents here. I am in the same spirit as Risa. I'm looking forward to discovering something that shouldn't be there and we don't expect, and that's a big electromagnetic signal from emerging black holes. And that'll really put us on our toes. Okay, so now is, I think, time for ask for questions from the audience. So there.
So on the topic of gravitational waves, I was just curious how often these events occur that we can detect. And then you mentioned during your talk that we stretch like a fraction of a proton. So I was curious, when those events happen, are we all stretching that little, distance?
Ryan, do you want to take a crack at that?
Right. So in the last 2 observing runs, we were detecting about 1 event per month when we were running, when both detectors were up. We're going down for some upgrades right now. We'll be back up in the fall next year. And the detection, the performance should be a little better. So maybe we'll get 1.5 per month, maybe as many as 2 a month. For the black holes, for the neutron stars, we still got to be lucky, but maybe we'll be lucky, right? Yeah, so that gives you sort of an event rate, so probably another 5 or 10 starting in about a year. For the strain, so 10 to the minus 21 strain over 2 meters, maybe, you certainly are getting distorted, but not very much. I mean, when you stand up, the compression is much bigger than from the passing gravitational wave. That's why the waves can get out from the inside of the supernovas, right? But it's also what makes them hard to see.
Okay, questions? Yeah, back there.
For the very largest black holes, what is the state of matter at the center?
Bob.
We'll be able to answer that question when we have a theory of quantum gravity. Okay, it's now a singularity according to classical general relativity, and to go to shorter distances, like 10 to the minus 33 centimeters, we have to merge quantum mechanics with general relativity, and there's various attempts now, which I won't go into.
Good answer. Okay. Yes, there's a question there.
What is the scope for sensitivity improvement in the gravity waves, and what will we be able to see if we attain, say, the maximum sensitivity that we might be able to achieve in the next, say, 10 years?
So, you want to talk about the scope, Brian?
Sure. So there are a couple of different possibilities for the improvement in the performance. We're about a factor of 2 to 3 right now away from the design sensitivity of advanced LIGO. And over the next 3 or 4 years, we should get very close to that as we increase the laser power and maybe put some squeezed light into the dark port, which is complicated, I'm not going to go into. We've got some new mirrors that are going in right now. Better scattered light control, a bunch of technical stuff, but a bunch of boring technical stuff, and some cool stuff like big lasers like Bob has been working on for us. That should improve our event rate, sort of the number of signals that we see. If you can see if your noise goes down by a factor of 2, you can see sort of twice as far out into space, and the volume of space you can see goes up by a factor of 8. So you make big improvements in the event rate and the amount of statistics that you can do collecting information about black holes and binary neutron stars and things like that. There are a bunch of us who are also working on next generation detectors. So instead of using glass mirrors at room temperature, you use big chunks of silicon at cryogenic temperatures. Or you put detectors out in space. Instead of having a 4-kilometer baseline, you have a 1.5 million kilometer baseline, so that you can see, with much better signal to noise, the kind of, the merger of the binary neutron stars that are coming in, so you can really study the equation of state. Or you can see bigger objects that are going around. There's a bunch of people who are working on making those longer term improvements, but that's, a question of funding and luck as well.
In that connection, we might also just say one more time that the radio technique, which looks at the very longest wavelength waves, which probably come from the best sources orbiting massive black holes, and those, there's a possibility of getting a detection of individual sources. The background is the first thing that should be seen, but that's a possibility. And then going even beyond the LISA horizon, which is essentially a telescope in space, is the possibility of either on the ground or in space. And something that people locally are doing is atom interferometry is a complementary technique. And if this could ever be pulled off as a gravitational radiation detector, it would fill in the gap between LIGO and LISA.
Can I mention one other possibility?
Please.
Which many of you know is being looked at right now. Theory of inflation, theory of the Big Bang, one of the theories of the Big Bang, predicts that gravitational waves could have been produced during inflation by the same quantum fluctuations that produced all the structure we see in the universe. And it predicts that there could be an imprint on the sky, on the cosmic microwave background of these gravitational waves. That's being searched for now, and we'll see what happens. There's various foregrounds which are a problem, but these are huge wavelength gravitational waves from the very early universe. So that's another thing I'd like to see.
Yeah. Back. Oh, yeah. At the back and then you. Okay. Yeah. Could you hear?
With the LIGO detector, how do you isolate out other noise in the environment? Like, the Earth is being warped by the moving tidal forces, buses driving past, or whatever. How do you separate out the gravity signal from everything else that we're getting?
Thank you for asking that question. So we have another hour, right, to talk?
Oh, another day, yes.
Yeah, so the question for those of you who are on the live stream is how do you isolate the LIGO mirrors from all of the stuff that's going on in the environment? And most of the time and money in the detector goes into doing that in one form or another. So it's a huge ultra-high vacuum system, so you get rid of all of the air, which is a huge source of disturbance. The detector band starts at about 10 hertz. We're only looking for signals above about 10 hertz kind of a frequency, so pretty fast frequencies. So when the moon goes by, it does stretch the arms by about plus minus 120 microns, but we just servo control that out. We just follow the ground distortion with the automatic control systems. At 10 hertz, the ground moves about 10 to the 9 times more than we want the mirrors to move. So we actually have 7 stages of isolation between the ground and the mirror. A bunch of them are just pendulums, so you have a mass on a string and you shake the top of the string and the mass doesn't keep up. We also suspend the mirrors off of big tables, so sort of not quite sort of round and about 6 feet across, these big seismically isolated optical tables. And those are hanging on springs, so you get some passive isolation. We also put servo controls on them. So we put little sensors in the tables, and we have a computer control system that watches the motion and pushes back. So as the ground tries to shake the table, we push back. And by using active and passive and feed forward and feed back and all kind of control systems, we are able to hold the table about 1,000 times quieter than the ground at 1 hertz. And the mirror itself, by the time you get to the end of those 7 stages, I said about 10 to the 9 times quieter than the ground. And we watch really carefully. Most of the data coming into the LIGO data stream is environmental monitors of one sort or another. So we watch how much the table's moving, we watch how much the ground is moving, we watch for cosmic rays, we watch for electromagnetic signals, we watch all kind of stuff for that. Yeah. If you want to work on that, you should come talk to me later.
Yes. So when asked to describe the motion of a cow free-falling in air, a theoretical physicist is going to say, well, first consider it a sphere, and then you have spherical cow theory. So I say this because I wonder about the statement that black hole is only described by its mass and its spin, and I wonder how the observatories and observations support or refute that hypothesis.
Okay. I'll take a first crack at that, and then maybe Bob wants to say something about it. I was careful what I said in that it's the sort that are going to be seen by astronomers. If you include the febrile imaginings of theoretical physicists, and I count myself in that group, then you can imagine a lot more types of black holes. Those that are endowed with charge, ones in different dimensions, and so on and so forth, ones in funny space-times, and all of that. This may seem like some strange diversion when there's the real thing out there, but it isn't, because it's actually been a touchstone for theoretical physics, and just asking these thought experiments about these black holes, even if you haven't got one in the laboratory, has turned out to provide just the right questions that have produced very interesting answers. Where this will all come together is the theory that Bob understands perfectly but didn't have time to explain, which is the theory of quantum gravity. And obviously then that's where a union will, an ultimate type of black hole, if you like, will happen. But we could say that there were charges in black holes, but if you think about them in astrophysics, they will almost immediately discharge. And so we really have no expectation to see, according to general relativity, anything that's described by much more than mass and spin. Bob, you want to qualify that?
Yeah. One very exciting possibility with LISA is to discover a star or a white dwarf or a neutron star or a small black hole orbiting a big billion solar mass black hole. Well, actually 10 to the 6th for this one, okay? And you can follow that with the gravitational radiation that LISA may discover, okay? And that little guy is a probe of the space-time around this spinning black hole, okay? It can measure the moments, the mass moments, which are predicted exactly, okay, by our present theory, and test That's going to be the best test, I think, okay, of black hole space-times, these orbiting small objects into the big one.
Okay.
It seems like there's been a lot of black hole mergers in a very short period of time discovered. Is there any thought that there's so many black holes out there that they contribute to the dark matter?
Research, I think.
I can give that a try. I mean, I think the answer is probably not. So the black holes that have been discovered are pretty low mass, right? As somebody, I work on very massive objects, you know, kind of thinking about the mass of the whole universe. So to me, they're very low mass, you know, sort of 30 solar masses. So almost all of the parameter space for objects of that mass to produce the dark matter has now been ruled out. There are some windows where basically early forming black holes could still produce some of the dark matter. And so I don't think that's totally ruled out yet, but I would not put my money on that.
Back. Back? Yeah.
Could each of you comment on what your hope is of these measurements and the theoretical studies that associate with them have towards our progress towards a theory of quantum gravity?
Gosh. I'm going to take a pass. Take a pass on that one. Okay. Bob? All right, I'll try something. One of the things I mentioned of, and I did not bring this up, is the possibility that there are mini black holes or primordial black holes with masses of about 10 to the 15 grams, about the size of a big mountain or something like that, and they could radiate, as Stephen Hawking originally showed, and essentially evaporate. Now, to make such things astrophysically is terribly hard, and we have no good, many people have actually looked for these, and there's no evidence that they exist. But let's suppose that they were actually discovered, perhaps by Fermi, for example, in some completely new window that we hadn't seen. Then that wouldn't be solving the problem of quantum gravity, but it would be an observational window on doing quantum mechanics in a curved space-time, and that would be a very interesting step along the way. But I, like Risa, I'm not terribly optimistic that we're going to see that, but it would be lovely to do it. Nicola?
Yes, just let me add something. I'm not going to talk about quantum gravity. But yes, as Roger said, these evaporating black holes would emit radiation and initiate a cascade of particles that in principle could be detectable, for example, in gamma rays. And even if, there are two strategies to detect this radiation. One would be to look into bursts of radiation that will happen when these black holes reach their end of their life. But also the contribution of the multitude of these little black holes could create indeed so-called diffuse gamma ray emission. So we are working on that. We put some upper limits, and when I use the word upper limits, mean we can constrain the number of these objects and their population.
Sort of following up on the question about the compression. The descriptions have been in terms of space, but we're talking space-time. So is there a time compression that's going on here that washes over us at the same time the gravity wave goes by?
Bob, do you want to? No, you go, Bob.
Yes, sir. Yes, there is, and I'll give an example. Okay, with this network of millisecond pulsars around our galaxy, okay, we're monitoring the arrival time of those signals from these dozen or so pulsars. Very good clocks in all directions in our galaxy, okay? And we look at the arrival times of those pulses and monitor all those arrival times. And in principle, we can detect a gravitational wave distorting the arrival time of those pulses coherently at the detector. And we hope then to get information about gravitational waves with periods of about a year, okay, from this pulsar timing array. Okay, so that's one example. Okay.
Good. Right at the back, over there.
So this is more of a visual, the simulation which we saw of the two neutron stars coming together shows a nice diffusion of those together instead of a violent impact like billiard balls or asteroid impact. Is there a reason for that?
Sorry, is the... Oh, sorry. Why it was done apart? Basically, what's happening, I think I couldn't quite hear the question. I think I understand it. Basically, what happens is if you've got two neutron stars like that, when they're about that far apart, which is just before they might merge, there are very large tidal forces that act like the force that the moon and the sun exert on the Earth, but very much larger. And they can be so large that they can pull gas off the surface of the neutron stars, and that then orbits around and swirls around. It's obviously terribly hard to measure that and to model that, because it depends on a lot of sort of detailed physics, but people are trying to do that. And then eventually what you get is what's left of the neutron stars, which is most of them, make a single collapsed object, which is probably a black hole, but there's enough gas swirling around to make a ring, a very thick disk around it. And then there's a larger sphere of gas, a so-called kilonova, that's expanding outwards, and that's what the optical astronomers like Risa and so on observe with their telescopes, and will presumably do the same again. Risa, do you want to? Oh, yes. So, yes. There we go.
And so what's the determination of those LIGO stations? Do they operate separately, or is there a central center to make decision of those strategic, of which specific location of those centers? Thank you.
Ryan, that's yours.
Right, so the detectors all run independently, but the data streams from each of the detectors, the two LIGO detectors and the Virgo detector in Italy, those are all combined with a few seconds delay. And it's really important to be able to do that because by combining the three data streams, you can do timing of when the signals come in, right? And so by looking at the relative timing at the millisecond, better than millisecond level, right, you can do triangulation to the source, right? And so that's how, by combining those, and that is actually done at a couple of places where we combine the data depending on sort of who's awake. You can get as rapidly as possible the source locations and send that out to all the astronomers. And I should say, in 03, if any of you are, in the next observing run number 3, if any of you are amateur astronomers, I know my boss is, those alerts are going to be public. So you can go and point your own telescope at the black holes and not see them, just like all these guys do, right? Or the neutron stars, and maybe see something pretty cool.
So I'll just follow up on what Brian was saying about the three detectors. One of the things that's so fabulous about that is you do get a much better positioning on the sky. And I think in this event, it was just incredibly lucky that all three detectors were actually able to see it and get information about it. If we actually get more detectors, then we can bring that sky area even further down. And that's exciting to me for the cosmology piece, because that means you might even be able to do cosmology with the black hole mergers. So right now, it's just the sky area is too large to be able to do that effectively. If you can bring that sky area down, and then you can actually probably take spectra of every single galaxy where the thing could have happened, then you can actually do cosmology in a statistical way using those measurements. So I think that's a really, really powerful thing for the future, especially if we have 4 or 5 detectors.
Yeah, and another thing that you get out of this network of detectors in the future is that you can use the polarization rather efficiently. You may remember I did this sort of business. the wave is going in that direction, and there are these two polarizations like that, and the sort of one like that, like that. And that is prescriptive of the source, and it's actually prescriptive of the physics, because we can imagine very different types of waves in principle. There's no evidence in any of the existing data for all the presence of these waves, but we can do yet more tests of the actual general relativistic description of gravitational radiation and how it's propagating from there to here. So far, it seems to be following the textbooks very well, but it doesn't absolve us from the probability, from the responsibility of performing those tests when we can. And that will be facilitated by having a large network of gravitational wave observatories, as well as the positions.
Yeah, I just want to add something along this line, that another very important thing that in future we really hope that through gravitational wave they could measure the orientation of the system with a high accuracy, and then if we in gamma ray we see emission from a not aligned jet toward us, then it would be already a discovery, because so far we thought that GRB, short GRB, had to point toward us. So in that case would be already something that we are looking forward.
Great.
In the near future, say 15, 20 years, do you see amateurs being able to get in on the game? Have there been techniques that were rejected that can now be brought back, now that we know the phenomenon is detectable?
So, Lisa, do you want to try that?
Yeah, I mean, I think the answer is yes. I think once the frequency of these things goes up, I mean, the main thing that you want to do is get, right now is cover as much of the sky as you can. So the more, I mean, it was really exciting how many observatories went to look at this thing, very, very quickly. So that was great. But the more observations we have of this, and the different cadences of observations are really useful, different depths, different wavelengths. I think it's likely.
Can I follow up?
Oh yes,
that?
please, yeah.
Getting in on building your own gravitational wave detector is going to be tough. But there's at least one opportunity. Actually, there are a couple of opportunities now for people to help with the data analysis. So, looking for these periodic sources that Bob was talking about. There's a project called Einstein at Home where you can, turn over some free computer cycles in your laptop to look for some of these sources. And also, there's a bunch of glitches in the LIGO detector, which we haven't fixed all of them yet. And there's a bunch of work to characterize and try and get rid of those by using neural nets and getting, again, some citizen power in with their computers to help, look and identify and hopefully fix some of that stuff.
So I know that the most recent one, you had like about 100 seconds of data before the final merge. So I'm wondering if at some point in the future, you'd be able to get several minutes advance notice, triangulate in advance, and then point all your optical and RF telescopes in the direction before the event occurs. I'm wondering if that's a possibility.
Yes. Yeah.
I think you're on that paper, so.
Sorry. Okay. I just wanted to mention that atom interferometers are proposed for the future of gravitational wave astronomy between a few millihertz and a few hertz. Okay? To eventually be put in orbit around the Earth is one proposal. Okay? Atom interferometers. Okay? And they could give you this early warning system, detect the binary, okay, well in advance, alert all the observatories, okay, and really learn a lot. So that's the hope in that frequency range.
Yeah, and the same can be said for, LISA, if and when that happens, and the pulsar timing array, which is very long because you could have a very long period radiation there. And so you could observe that for a long period of time, long before a merger.
Question for Bob. Excuse me if I'm implying that we're on a first name basis. You mentioned something about bumps on the surface of a rotating neutron star. I'm trying to understand, I'd never thought about whether the surface of a neutron star or a black hole is uniform.
Okay. Yes, this is an example, but it's very difficult to make a mountain on a neutron star. Okay, the surface is a solid. Okay, gravity's very strong. Okay, so it's very difficult. If you have extremely strong magnetic fields, you know, that's part of the way there. This is really just an example, not my favorite source, but that's one possibility. But there haven't been any detailed, believable proposals. Roger should comment on this one for making little bumps. You know, really little bumps are enough on a neutron star to radiate.
I mean, I agree with Bob. The best salvation, the last refuge perhaps of a scoundrel, is an enormous magnetic field in the interior, and that's the best I think you could hope for. But it's, you know, it's on Reese's list of surprises. It could be there, and you're, you know, maybe this would happen in a very newly formed neutron star in a supernova explosion. Even that's a possibility. So, you know, there's a lot of discovery out there.
What's the wavelength of a gravity wave?
Yeah.
I make a little. Sorry. Let me just throw out a little back of the envelope thing. Okay. You can show fairly simply for any bound gravitational system at all. Okay, any bound gravitational system, bound by gravity. You can show that the highest frequency you should observe from such a source will be of order 10 kilohertz. Okay? And the lowest frequency is Hubble, essentially. Okay? And I can't resist another back of the envelope thing. You can also show that the maximum luminosity that any bound gravitational system can radiate in gravitational waves is the speed of light to the 5th power divided by Newton's gravitational constant. That's it. 10 to the 54 watts. A lot of light bulbs. 100 times more powerful than was seen in these sources, okay? And 1,000,000 times more than all the stars are radiating right now in the universe. Okay, so that's a little tidbit I couldn't resist throwing out there.
Okay, we've only got time for a couple more questions, so we'll have 2 more questions. One there at the back.
That's for 8 feet.
So, actually related to the question about the wavelength of a gravitational wave. So once you've converted, let's say, 3 solar masses into gravitational wave energy, over time, how does that dissipate, or what other forms of energy can that convert to? Or is it only the fact that space is expanding, so the wavelength will increase, therefore the energy will go down?
Yeah. You want to, I mean, I'm going to say, why don't you do that, Bob? Yeah. Yeah.
I didn't get the first part in detail, but
So how do
the
you
gravitational
dissipate?
wave will leave the source at a fixed, some spectrum, okay, a wavelength and frequency, okay? And in the expanding universe, those wavelengths will be stretched just like photons, okay? They're going at the same speed, they have the same properties. It's just spin 2 versus spin 1. No big deal, okay?
So other than that, there's no other way to dissipate the energy that's in a gravitational
No, because on the good side, gravity is so weakly coupled to matter that we can see in gravitational waves right back to the Big Bang, unlike neutrinos, photons, or anything else. Okay, that's the good side. The bad side is it's hard to detect. Okay.
Yeah. But the dissipation is very, very hard to arrange, except, as you say, in the expansion of the universe, which is not a dissipation, but it's just losing energy like the microwave background does. So, final question. Anybody? Okay, sir.
In your talk, you mentioned the spin of black holes. Some spin very quickly, some more slowly. Can you give us some idea of a range of these spins and how you calculate that and measure it?
Okay, there's a way of thinking about the spin of a black hole, and according to orthodox general relativity, there's a maximum spin that you can have for a given mass. And it basically means in Bob's order of magnitude sense that some spaceman, by spaceman Kip, for going around just hovering above the surface, would be moving, you would measure that speed as being close to the speed of light. That's one way of thinking about it. So in the case of, black holes and galactic nuclei, we're talking about periods of about an hour or so, maybe. And the ones in smaller ones are periods of milliseconds. So those are, that's a limit in orthodox relativity of the sort of black hole masses you might see. So some black holes are going to be spinning very slowly. Others are going to be spinning very fast and have a lot of energy associated with them. Up to 29% of the rest mass energy of a black hole in principle is there for the taking. So it's a big reservoir, and that's why we think it can explain these jets and so on. Well, look, I think we've had many truly excellent questions. I thank you for those. And do you want to say just a few words?
So I just wanted to thank everybody here for being such a fantastic audience this evening. It really means a lot to us to have such an enthusiastic crowd. Now, we hope to see as many of you as possible on December 12th for Professor Aaron Rudman's lecture on the fastest eye on the sky. But for now, please join me in thanking Roger, Nicola, Risa, Bob, and Brian one more time. Have any last burning questions on the way out?